Good afternoon. I am Andy Nguyen with the University of Texas Medical School in Houston. It's my pleasure to have an opportunity to share with you the results of our study on automated lymphoma diagnosis using host-line imaging and deep learning. For the outline of this talk, I will first define application of deep learning method, a technological breakthrough in machine learning to big data analytics. I would then move on to the main part of this talk, automated lymphoma diagnosis using digital images. I have no relevant financial relationship with commercial interest to disclose. Machine learning is software algorithm that can learn from and make prediction on data. That is, it gives software the ability to learn without being explicitly programmed. There are numerous machine learning methods, such as decision tree, cluster analysis, support vector machine, random forest, Bayesian method, regression analysis, neural network, and so on. Deep learning is the most recent and most disruptive method of machine learning, and it is based on neural network. Big companies are analyzing large volumes of data for business analysis and decision using deep learning technologies such as Google search engine, Google Photo, automobiles companies with self-driving cars, and IBM Watson. The application of deep learning to digital pathology image has a very promising start, and it could impact personalized diagnosis and treatment. Deep learning is based on neural network. Neural network is inspired by biological neural network. It consists of artificial nodes known as neurons, and they're connected together to form a network for prediction and classification. This diagram shows the data input being fed into a neuron. Each data input has an associated weight. The sum of the input with associated weight is passing through an activation function. Depending on the result of the activation function, whether it's above or below a certain threshold, the neuron either fire or does not fire. Early generation of neural network with supervised training is shown on the left diagram. Input data are fed through input vector, and they propagate through hidden layers in the network to produce result which is positive or negative. And this output will be compared to correct answer to get the error signal. A method called backpropagation is used to get derivative for learning. Early generation of neural network has two main disadvantages. First of all, parameters often do not converge, and this yield no solution for the network. Secondly, the model does not scale well when there are many hidden layers added to the network. Deep learning with third generation neural network is a major breakthrough in deep learning. It started in 2006 and helped it to outperform all the other machine learning models. Deep learning algorithm is based on unsupervised learning. It allows a network to be fed with raw data with no outcome and to automatically discover the representation needed for detection or classification. It extracts high-level and complex data representation through multiple layers. And this avoids the problems of previous generation network shown in previous slide. The key element of deep learning is the supporting hardware in the form of multiple graphic processing unit known as GPU. A GPU allows for multiple parallel processing, which is very important in matrix manipulation in image analysis and processing. Lymphoma is a clonal malignancy of lymphocytes, either T or B lymphocyte. The WHO classification of lymphoid malignancy includes at least 38 lymphoma entities. Lymphoid malignancies were diagnosed in about 300,000 people annually worldwide. Lymphoma is typically first suspected by their pattern of growth and the cytologic features of the abnormal cells through light microscopy of hematoxylin using stain tissue section. Immunophenotyping by flow cytometry with or without immunohistochemical stain are required for diagnosis. Additionally, cytogenetics, molecular results, and clinical features are often needed to finalize the diagnosis in certain lymphoma type. Due to subtle difference in histologic findings between different types of lymphoma, histopathologic screen often present a challenge to the practicing pathologist. Therefore, an automated diagnosis for digital image could be very useful to assist the pathologist in daily work. Previous attempts to digitally classify histologic image were based on specific criteria such as nuclear shape, nuclear size, texture, etc. Typical parameters are shown in the right inset here. Note that up to hundreds of parameters have been used in such classified software. However, they were not shown to be very successful. Subsequently, attention has been turned to machine learning, and in recent years, deep learning techniques, especially the third generation neural network called convolutional neural network, short as CNN, has quickly become the state of the art in computer vision. Now, CNN is inspired from the primate visual cortex. The ventral visual pathway is organized as a series of 4 interconnected visual areas called Brodmann areas. A neuron in early areas such as area V1 respond to relatively simple visual features of the retinal image, while later areas such as area V4 respond to increasingly complex visual features. The specialization of receptor cells are incorporated into the design of CNN as pairs of convolution operator followed by pooling layer, the details of which will be described in later section. The left image shows a rough correspondence between the areas associated with the primary visual cortex and the layers in the CNN network. Let's talk about convolution. Convolution is an operation in image processing using filters to modify or detect certain characteristics of an image, such as smoothing, sharpening, intensifying, enhancing. In CNN, it is used to extract features of images. Mathematically, a convolution is done by multiplying the pixels value in an image patch by a filter also known as a kernel matrix. The result is called a dot product. By moving the filter across the input image, we can obtain the final output as a modified filter image. The convolutional layer performs feature extraction consecutively from the image patch to higher level features. The max pooling layers reduce image size by subsampling. And finally, the last fully connected layers provide prediction for the network. Recent studies have shown very promising results in using machine learning to detect malignancy in whole cell imaging. However, they were limited to just positive or negative results for a particular neoplasm. A very good example is the presence or absence of carcinoma in secondary lymph node in breast cancer. In this study, we attempt to explore how deep learning can be used to accurately classify a test case as one of the four entities which are representative of various morphologic patterns in lymphoma. They are shown in this slide: benign lymph node, diffuse large B-cell lymphoma, bucket lymphoma, and small lymphocytic lymphoma. The digital image source for our study coming from two main sources. The first one is from the virtual pathology at the University of Leeds. Up to 356,000 slides are available on this site. A web browser is used to view the image, and we use a software Snagit to capture and automatically save 40 by 40 image patch into a file in JPEG format. The second data source is the virtual slide box at University of Iowa that has about 1,000 slides. We use BioLucida Viewer to view the image and also use Snagit software to capture and automatically save 40 by 40 image patch in the JPEG format. Whole cell imaging is typically obtained with Apero instrumentation. Our study includes 32 cases for each of the four disease entities: benign lymph node, diffuse large B-cell lymphoma, bucket lymphoma, and small lymphocytic lymphoma. We use four sets of 5 representative 40 by 40 image patch for each of the 32 cases. That gives us a total of 2,560 images for the whole study. Our programming platform is done with the Python language, a very commonly used software in deep learning. We also use TensorFlow and Keras library on top of the Python language. Keras library allows for parallel computing using GPU with associated libraries. The hardware is based on Intel, running on Windows 8 64-bit. We also use GPU by NVIDIA, supported by Compute Unified Device Architecture, known as CUDA. And this allows for multiple parallel processing of matrix. For validation method, we use about 70% of the image for training, 20% for validation, and 10% for testing. For each of the test case, we use a process called majority voting. That means that the predict diagnosis for each test case is obtained from 5 images, and at least 3 of them have to agree in order to obtain a consensus. The first example on the left here show that 4 out of 5 image patch give prediction of diagnosis 0, and example 2 show that all 5 out of 5 image patch give the prediction of diagnosis 1, and the last case show 4 out of 5 image patch agree on diagnosis 3. For the results of this study, we show how accurate the model can predict the diagnosis. The first table shows accuracy using image by image prediction. Each row here show predicted diagnosis, and each column here is the actual observed diagnosis. And the accuracy of the model is obtained by adding all the number on the diagonal of the table here. And it shows accuracy of 95% if we use image by image prediction. If we use majority voting, which means case by case prediction, the accuracy go up significantly to 100%. In summary, we explore how deep learning can be utilized for histologic diagnosis of lymphoma using whole slide imaging. Deep learning with CNN algorithm use very impressive result of 100% accuracy. Generic machine learning algorithm with CNN give us the ability to apply this to different type of malignancy, GI, GYN, etc. because we have no need for manual setting of morphologic parameters such as nuclear architecture, shape, texture, etc. Our current model has two main limitations. First of all, only 4 histologic categories were included. Clearly, it is not yet practical for clinical use because lymphoma has at least 38 disease entities. Secondly, representative image in a model require manual selection of suspected area. A future study would need to have more automated method to obtain suspect area. Regardless, our prelim study provided a proof of concept for incorporating automated lymphoma diagnosis using digital microscopic image into the pathology workflow to augment the pathologist's productivity. Future studies will need to include more histologic entities and many more cases for training and also for validation. At this point, I would like to acknowledge the contribution of my colleagues in the section of hematopathology in the Department of Pathology at University of Texas Medical School in Houston, Dr. Lei Chen, Chi-Hong Hu, Dr. Amir Wahid, Aris Wang, two of our residents, Hanadi El-Achi and Tatiana Belusova, also two colleagues from oncology department, Dr. Zed Kanan and Adan Rios. Thank you so much for your attention. At this point, I would like to open the forum to questions and discussion. Thank you very much.